Hi folks, I wanted to make this video to show the demonstrations that were done in class on Monday, November 9th, for those of us that weren't able to make it to class. These demonstrations are referenced a few times throughout that lecture, so if you're following along in the lecture and you hear me talk about just like blah blah blah, that demonstration at the start of class, these are those demonstrations. So hopefully maybe you even paused the video, went over to watch this one, and then came back. I'll try to remember to put in the description of the lecture video a reminder that this video is posted so we can watch those demonstrations. Now, what I have here is a galvanometer, which is a large, I should say it's large because it's a classroom demonstration galvanometer. In lab this week, you'll use some that are just as big as what's on a tabletop. But this will measure current. It uses the torque on a current-carrying loop of wire. In order to do that, there is a square, or not a square loop of wire, but a loop of wire that has a magnetic field kind of skimming along that surface, so that when a current runs through that loop of wire, it either orients in one way or the other, so that its induced, so that its magnetic dipole moment aligns itself with the external field. Now, right now, so that will allow us to determine the direction of the current, whether it goes one way or the other, and the extent to which that twisting occurs. The torque on it will tell us how strong the current is in that magnetic field. Now, right now it's reading 0 amps of current. And even then, I don't know if this is, it depends on what the settings are on the back, whether it's amps or milliamps or whatever it is, but 0 units of current. There's no current running through this coil of wire. Now, this coil of wire happens to be placed in a region with a very large magnetic field. The magnetic field through the poles of this permanent magnet is right through the middle of this wire. I can show you that this is a nice strong magnet if I take my keys, and you can see that my keys attach themselves to really my keychain. These are brass keys, but my metal keychain attaches itself quite easily to that magnet. So I have a very strong magnetic field right through my loop. But that does not mean I have a current. So even though in today's class we talk about the magnetic flux is through the center of this loop and rather large, there is no current. Now watch what happens when I pull the loop out of the field quickly. As I pull the loop out, you see that the current changes. Now I can pull the loop. Let me white balance this a little bit better. We'll turn off my secondary monitor. There we go. Maybe we can see this a little bit better now. As I push the loop in, watch that current needle. We see that I have current in one direction around the coil, and as I pull it out, current in the other direction. In, out, in, out. So as I introduce the field, current goes around the coil in one direction such that it goes into this wire over here. As I pull it out, current goes around the coil in the other direction so that it goes into this wire. Now I'm going to, watch very carefully, I'm going to give this a grilled cheese flip, 180 degrees. Now I'm going to introduce, and it used to go to the positive direction, but now when I introduce it, it goes in the negative direction, and then when I pull it out, it goes in the opposite direction. So that change is due to me changing which way the coil is oriented, not necessarily changing the increasing or the decreasing magnetic flux through the surface, but changing which way it went around the wire wrappings, right? The wires are wrapped in a certain direction to either feed into one port or to feed into the other port. What's important is the direction of the current changing when I am increasing the magnetic flux or decreasing the magnetic flux. Here I am increasing the magnetic flux because now there is magnetic flux when out here there was none, and vice versa when I pull it out. So that's one demonstration that we did. This really motivates our discussion of Faraday's law and Lenz's law, that a changing magnetic flux through this coil, by there suddenly being a magnetic field when I put it in there versus when there isn't a magnetic field, that changing magnetic flux sets up a current that can actually go around these wires and be measured by a galvanometer. Now the other demonstration that we did involved, I have it over here, right? This, I have to make sure that keep this magnet away from this magnet, so let me just move things around a bit. Here I have a little rare earth magnet, a neodymium magnet, and I have two pipes right here. Well, we'll start with this PVC pipe. Give me just a second to move this down out of the way. We have a PVC plastic pipe. Now this is not a magnetic material, so I'm not at all surprised when this magnet doesn't attract itself to this PVC pipe. Now what happens when I drop the magnet rather through the pipe? So I'm putting it in the top here. I'm going to let go, and it came out, right? So if we were to count, not even a second, right? I'll let you know when I let go. 3, 2, 1, drop. Whoops, missed it. Attached to my coffee cup. I was hoping we could catch it on video being there, right? It just drops through the pipe. 3, 2, 1. Whoops. 3, 2, 1. Release. And it drops through the pipe. It takes no extra time to fall through the pipe because it certainly, let me see if I can get right, is not as big as the pipe. There's extra room there for it to wiggle around, so there's no friction, right? It's smaller than the pipe, and it falls right through the pipe. Not too surprising. Here I have a copper pipe. Now, copper is a conducting material. That turns out to be important, but it is not magnetic. This does not, it's not attracted to the copper, right? It's not one of the permanently magnetizable materials, iron, nickel, and cobalt. Those ones are magnetic, so steel, which has iron in it, or alloys thereof. This would stick to like a fridge door, but it doesn't stick to, if our fridge were made of copper, it doesn't stick to it. Now I'm going to show you that again, this magnet is not as big as the pipe. So it still has room to wiggle around in there. So it's not going to be friction was about to happen. But as I put we'll do the long view, as I put the magnet in, it's falling. It does get caught up on the end there, just at an angle. It's falling, but it doesn't fall nearly as fast. I'm not sure if the microphone is picking it up, but it takes its sweet, sweet time to fall all the way down. I'll flip the pipe around. It's falling right now, but it is not falling as fast as it was in the PVC pipe. And in fact, when it leaves, then it kind of speeds up because the pipe is slowing it down. In lecture, we talked about the creation of these tiny induced magnets, both below it and above it as the magnet falls. We used Lenz's law to describe the direction of the induced magnetic fields due to the induced currents, and we can actually describe why this magnet falls down due to creating tiny little magnets below it that oppose it and push it up, and tiny little magnets above it that attract it and pull it up, both of which contribute to this 3, 2, 1 release. This slow, 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 slow process of it falling. Let me see if I can actually get it to show up on the video. I've never tried this, so let's see. We're going to point this up. And if we can look down the pipe. Oh, this is going to be great. So now I'm going to release this magnet, and you can actually watch it float down. Now I'm going to move it at the last second so that it doesn't hit my camera. We can watch it float down, and you see that it's not touching. It's just slowly coming towards. I don't want to bust my camera. Let's look on the top down as well. Let's see if I don't know if this will be as easy to see. It's almost all the way out. I don't know where my camera is. Let me first play around with. Okay, there we go. I want to hold it just like that. Look at this, just perfect. There we go. Now we'll place it in. And you can watch it fall slowly, slowly, slowly down. Reducing its speed because of the induced currents and the induced magnetic fields both below it and above it, and that we do discuss in class. So I wanted to show you those lectures, those demonstrations that we showed in lecture for those of you that weren't here today. Excellent work, everyone. Keep it up. Ask questions when you have them.